Hi everyone, I'm Samet. So I will talk about SGD and essentially some nonlinear dynamics. So, the basic motivation is dynamical systems appear all over the place, like from physical systems to reinforcement learning control problems to NLP applications. And obviously, like they are typically super complex. There can be like spatiotemporal dependencies, especially in complex systems or networks. And the talk today is essentially just like taking a very simple nonlinear dynamical system and trying to provide efficient learning guarantees. So essentially the system we are considering in the more general form, I will simplify it in a minute, this is still too complex, is a state equation. So suppose I observe the state and I have an evolution as a function of some function f. So I have a state vector, I have an input vector, and I can have noise, and they can be all nonlinear. So let's simplify it even further. I will focus my interest to some matricized equations. It's parameterized by some A and B and some activation phi. Phi applies entropywise. So this connects to linear dynamical systems as well as recurrent neural networks. So what is our problem setup? I will just take some input sequence that I know the sequence myself, and I will just drive the system with this input sequence, and it will generate some H, and the system will evolve according to A, B, and phi. And I will assume that A and B are unknown, which I want to learn. It is a parameter estimation setup, essentially. And activation phi is known. Okay. So my goal is essentially finding these unknown parameters A and B. So what I will do is pretty simple. I will just formulate a regression problem. I will just set my input data to be concatenated state vector and input sequence UT. So here mu is a scaling term. It really doesn't matter. So what matters is input is just the concatenation. And then I will set a quadratic loss to fit to the next state, and I will start running SGD. And the ideal solution that I want to find is this theta star, because it essentially sets the loss to 0. So notice that I even remove the noise. It's pretty simple. I'm in the setup. So what are the challenges here? The possible challenges are there might be temporal dependence, and another question is, can I get optimal sample complexity? So what I will do first, before stating our results, is I will do another assumption, which is essentially an assumption on the activation function. The results will apply to activations with a slope. So these are increasing activations where the slope is positive. Okay? So I cannot do ReLU, but I can do, for instance, leaky ReLU, where there is some kind of small slope, some slope beta. Or I can essentially convert any increasing activation to this kind of activation. Okay. So the reason I'm assuming this, there are a couple of reasons, but the main reason I'm assuming this is, since this is a parameter estimation setup, I want to be able to learn the parameters. And essentially, I want to ensure that this Hessian is positive definite. And this beta increasing activation is essentially one way to guarantee that there is a non-trivial case. In other words, if I drive the system by Gaussian input, then states will have good covariance, and then Hessian will be nice, and the problem is solvable. So that's the intuition. So long story short, here is the main result. What I will do is I will assume this system is stable, in the sense that spectral norm of the state matrix is bounded, and activation is beta increasing and inputs are Gaussian. And then let's define a condition number kappa on the state covariance, where we know that we can bound it because the activations are nice. And then if the trajectory is approximately greater than n plus p times condition number, then starting from any initialization, SGD exponentially or linearly converges to the grand truth solution, which is A and B. In other words, this theta tau will converge to A and B, and the error decays exponentially fast. So what are the takeaways here? We achieve linear convergence. We achieve near minimal sample complexity, in the sense that if you do a simple parameter counting, you will see that we have, in total in A and B, there are n times n plus p unknowns. And after a trajectory of length n, I observe the system for capital N duration. I will have n times n equations. So as a result, I need capital N to be larger than n plus p, which is exactly what we get in the result. And finally, one drawback is essentially as the system becomes more and more unstable, as it becomes like closer to 1, the spectral norm, then essentially the bonds get weaker, which was not reflected in the theorem, but that's just the reality. So, but another thing is essentially if I get to have access to, let's say, multiple IID trajectories, so one challenge is essentially the temporal dependence. If I have many, many IID trajectories, then obviously I can even say something about unstable, in other words, blowing up systems as well. So, so these are the takeaways. So let me just describe our approach. So how are we going about this? So essentially the key ideas are essentially pretty simple. So what I will try to do is, originally I have only single trajectory. I only see like one trajectory of the system. But the question is essentially, perhaps I can take the single trajectory and create some kind of IID, nice empirical risk minimization problem. And to do that, I can leverage stability and mixing time arguments. So essentially, if A is, the spectral norm of A is less than 1, then the faraway samples will be approximately independent. So perhaps like the state evolution is like this line, the dashed line. And then if I subsample it, then they're kind of IID. And as long as the subsampling rate is not that bad, I can get away with it. So long story short, I mean, the main idea that can apply to kind of any system, any stable system, is I start from my original data, which has perhaps temporal dependence, subsample it to get weak temporal dependence, and then I apply a truncation trick to kill the tails, to kill the impact of the previous state to get IID samples, like temporal dependence to IID samples. And at that stage, essentially, it is just a statistical learning problem. I can go from IID samples to infinite, like population, essentially, using uniform convergence or concentration. Okay. So just to rigorize what is the truncation trick, it is essentially, suppose I have a sequence HT, but now I can define some auxiliary state H bar, which essentially forgets the previous L inputs. I just, not the previous L. It only keeps the most recent L inputs, but forgets the rest, okay? So this is the truncated state, and you can essentially show the nice properties of this. First of all, the gap between truncated state and the state decreases exponentially fast in L. And secondly, the samples I generate, U and H bar, are literally IID. As a result, U and H becomes almost IID when I subsample it. So obviously, this strategy, I mean, mixing times stability arguments, these are like classical ideas, I would say. So it's like, Binu has a nice paper. So recently, Mozart and John Miller, they used it in an ICLR paper to show some stability of recurrent neural networks. And actually, there are like very interesting work going on in this space, especially in the context of linear dynamical systems, by papers by Ben, Sasha, and Ambuj. And also, you should definitely see the RLN control session on Friday. So there will be some ideas over there as well, I'm pretty sure. And in summary, the conclusion is, so we show some statistical learning guarantees as well as optimization guarantees for SGD for nonlinear state equations. So the key idea is essentially going from temporal dependence to IID sequence. So overall, I would say essentially the setup is fairly simplistic, and there can be like many interesting directions. For instance, like there's not even noise in the system, so it would be interesting at least there's noise. So that would, I mean, beyond other extensions. Like, I mean, we can also add output measurements, perhaps general dynamics, or maybe addressing ReLU and control problems. Yeah, thank you.